Well, if that's right or right, it kind of does make sense. When you live in a very temperature temperature world where we're very familiar with changing temperature, well, what about changing pressure? You know, I guess what comes to mind is like a bike tire and a bike tire pump, right? The tire volume doesn't really change too much, but you're putting more molecules of air into a fixed volume. So it's molecules per cubic centimeter, let's say. It just comes to the top of my head. So that's pressure. And vacuum pumps find different ways for different levels of vacuum, but to remove molecules of air per cubic centimeter, let's say, the less air molecules, the less pressure. More vacuum means a lower pressure. So just a quick Google search to see if anything pops in for us to ponder, and not really, which is really strange. There's a lot of talk about, heat of fusion going across this boundary. You have to add a lot of heat in order to go before you can transition. But what about pressure? Like coming up at 100 degrees, you're in vapor. You have to increase pressure to get to a water state, a liquid state. But do you have the same type of phase boundary where it takes a lot of energy of whatever that is to make that transition? Or do you have to take out a lot of energy to make that happen? Kind of strange that there's nothing. They don't teach this stuff in science class, and it's not easily Googled. So you wonder what the hell's going on with that. Anyway, so we made a copy. Let me put it down here. Same diagram, but this pressure. You changed the what did we change? The temperature on the x-axis. We made that pressure, and down here, right? And pressure is, we said, going to be energy. So let's just, it's not going to be breath length. This is going to be something we don't know what it is. And where we put heat, we added heat to get the temperature to rise. What do we add in order to increase the pressure? And actually, it's probably opposite, right? This is probably low pressure, and this is high pressure. This is like 1 over pressure type of graph. All right, so let's change this to what we said. We said molecules per cubic centimeter. So that's how you impact pressure. The more molecules per cubic centimeter, the higher the pressure. The lower the molecules per cubic centimeter, the lower the pressure. We could redraw this, but let's just, for shits and giggles, for poops and giggles, 1 over pressure. So inverse pressure. So lots of few molecules per cubic centimeter would mean no, because then at a high one, this is few. So at a lot of, no, because then this would be 1 over that also, because this is lots of molecules, not a few. So this is inverse of that. It'd just be easier to like redraw the diagram, but for some reason I'm resisting doing that. All right, so let's say 1 over molecules per cubic centimeter. So 1 divided by 1 over. So this number being very big means a big number means very few molecules per cubic centimeter, because it's 1 over. Right? So 1 over a few is a big number. 1 over 1 is 1. 1 over 0.2 is a bigger number. It just like makes it hard to wrap your head around it. So at very few molecules per cubic centimeter, you'd expect a gas. This would be a big number because it's 1 over that. So that would be that. And the pressure of a gas you would expect to be low. So this is 1 over pressure. So low pressure, 1 over a low would mean it's a higher number on the graph. So I guess that kind of works. Something happened there with, I had to restart the voice recorder. So down here you have a small number, which means the molecules per cubic centimeter would be very high, thousands, to get a low 1 over. And then the pressure would be very high, so 1 over a high pressure would make it a low number on this graph. So the axes kind of work out. Let's see what all that means. So we have a high pressure. Let's say we're going the point of fusion, going from a solid to a liquid. So we have high pressure, high molecules, and we're saying that we have to increase the 1 over, which means smaller and smaller molecules per cubic centimeter, until you get to this point, which would then allow the pressure, or 1 over the pressure, to get higher, which then really means pressure is getting lower. So, you know, that's an interesting thing. It's not much talked about that I can find. I've never learned about it. It's not an easy, quick find on Google, that when you're crossing that phase boundary from a solid to a liquid by changing pressure and not temperature, do you get the same type of effect where it takes a lot of work or energy or movement before you get to the next phase? There's some time involved for all that to happen.